Over the course of your life, you may have come across hexadecimal numbers. You know, those weird numbers made out of digits and letters? How bizarre is that? How can you have E cars, 2C items in a set, or 12 carrots? In the history of humanity, a long time ago, we invented writing. And when we counted things, we started associating a written symbol to a quantity of items. Let's associate this quantity to this symbol, this quantity to this symbol, this quantity to this symbol, and so on and so forth. Let's not forget the absence of quantity, which appeared later. But very quickly we ran into a problem. This couldn't go on forever. We would have to create and memorize one distinct symbol for every possible quantity. That's just not doable. So we came up with a trick. We chose to stop creating new symbols after an arbitrary number. We decided that after the quantity 9, we wouldn't create any more new symbols. There would be no symbol for the quantity 10. Instead, we would consider this heap as one group and mark to the side that we have counted one group. The group is full, remains 0 grain. Funnily enough, we don't have a symbol to represent the quantity 10, but we do have a dedicated word for it, the word 10. We don't say 10, we say 10. Okay, then we keep adding grains. We now have one group and one grain. After 10 more grains, we memorize that we have formed two groups, and we keep going. So we found a way to count more than 10 items with no more than 10 symbols. Fast forward a few millennia. Back in the days, cars didn't have digital displays. Still, they needed a way to record the total mileage of the car. Car manufacturers came up with this clever little device, and I'm sure many of you are old enough to have known one. It's a set of cylinders with numbers from 0 to 9. You start driving, you drive 1 kilometer or 1 mile, then 2, then 3, up to 9. Beyond that, the second cylinder remembers that the first one has made one full revolution, and you keep going. After the second cylinder has made a full revolution, the third cylinder remembers that as well, and you keep going. Now here's the thing. Back in the days when we chose the number 10 to stop creating symbols, and we decided that 10 was instead one heap, 10 was chosen arbitrarily. It could have been 5, could have been 11 or 23 or 2 for that matter. We could very well have decided that 2 grains would make a heap, register one heap, and keep going. Had we decided so, the cars would have counting cylinders with only 2 digits, 0 and 1. No other numerical symbol would exist. Drive 1 kilometer, that's 1. But if you drive another kilometer, well, that's it for the first cylinder. You're already back to 0. The second cylinder registers one full rotation of the first one. Then you keep driving. And when the second cylinder moves again, well, it's already back to 0. So the third cylinder registers one rotation of the second one. And you keep going. I mean, it works. We are simply not used to count like that, but the math works the same way. The number of digits on a cylinder is called the base. It could be anything really. 2, 3, 4, 5, 6, 7, 8, 9 or 10, which is the one we're used to work with. None of them is more complex or complicated than the other. We're just used to base 10, that's it. But then why stop at 10? We could have more digits per cylinder. 11, 12, 13, 14. The thing is, we've never invented a symbol for the quantity 11 or the quantity 12 or 13. Those symbols were never created in the first place, simply because we arbitrarily chose to stop at 9. It turns out, in some cases, especially in IT, we figured that using base 16, which we call hexadecimal, was more convenient than the traditional base 10.
Hexadecimals to the rescue.
But these symbols didn't exist. We had to invent them. And that was a problem. What to put here? We could have used existing symbols or created entirely new ones. But that's difficult to apprehend when you're not used to it. Is this digit greater or smaller than this one? That's when we used another clever trick. Instead of creating totally new symbols out of the blue, we simply used letters. A, B, C, D, E, F. This trick has two advantages. Everybody knows the alphabet, so the symbols are already familiar to us, and they're already ordered. Intuitively, A is smaller than B, and B is smaller than C. And the cylinders work just the same. Start driving, drive 1 kilometer, 2 kilometers, 3, 4, 5. So far, no difference between base 16 and base 10. 5 in base 10 is also 5 in base 16. And you keep going. 6, 7, 8, 9, up to 9, no difference. 9 in base 10 is also 9 in base 16. But then base 10 runs out of digits. It has completed 1 full revolution and gets back to 0. The second cylinder has to memorize 1 full revolution. Base 16, however, hasn't run out of digits yet, so it keeps going. And that's how 10 in base 10 is A in base 16. It's the same number. You have driven the same number of kilometers. But depending in which base you write it, it can be written like this, or like this, or like this. Then you keep going. 1 more, 1 more, 1 more, 1 more, 1 more. And finally, base 16 runs out of digits as well. You drove 16 kilometers in base 10, or 10 kilometers in base 16, or 10000 kilometers in base 2. What happens next? 1 more kilometer, that's 17 in base 10, and 11 in base 16. Yep, that's right. These are 11 bananas in base 16. These are the same numbers, just written in different bases. That's it. I hope this little explanation will have enlightened you. Don't hesitate to tell me what you think in the comments. Cheers, bye.